Hi everyone, welcome back. You're watching the sixth lecture of EE635 Applied Linear Algebra. This is the third and final module. I'm Debasattam, and we have been looking at this rank nullity theorem, which I have said that is one of the most celebrated theorems of all of linear algebra. We've already seen rank nullity theorem in terms of a general matrix. What we're going to see here in this module is the rank nullity theorem in terms of something that is the generalization of these matrices. Okay, so without further ado, let me start. Let's start with the proceedings. Yeah, so I will share my screen. It should be up any moment. Yeah, here we are. Okay, so so think of matrices. Okay, uh, so as we have seen before, A is, let's say, a matrix from of size m cross n. See, I can take um, a vector, say x in Fm, and because my internet connection is not so good, let me switch off my video. Right. So x is some vector in Fm, so it's an m tuple. Notice that I can do this multiplication ax, right? And this ax in that case will be a vector in, oops, sorry, I made a mistake. This is n tuple, too bad. It's n tuple, and this multiplication produces a vector in Fm. So that way, this multiplication is in fact mapping from Fn to Fm. That means it takes a vector here and maps it to a vector here, right? This mapping is special because it satisfies certain nice properties. You see, if I take two vectors and I sum them, and then I make A act on them as a mapping, the law of matrix multiplication tells us that this is nothing but A times x1 plus A times x2. Notice that this plus is happening in Fn, whereas this plus is happening in Fm. So this is happening in the domain of A, this is happening in the codomain of A, right? But A in a way distributes over x1 over the addition in the vector space. Similarly, if I have a scalar multiplication alpha x and then make A act on it, this from the law of matrix multiplication will be this, which means, see, this is product in the scalar multiplication in Fn, this is scalar multiplication in Fm, but once again, you can interchange the two processes. This leads to this idea of the generalization of such mappings, namely the so-called the idea of linear mappings, or more formally, linear transformations. Okay. So what is a linear transformation? So we have a vector space V, a vector space W, both are over the same field F, all right? And suppose phi is a mapping from V to W such that any vector V is sent to phi V, which is, say, we define it as W, small w. Yeah, and it's said to be, so phi is called a linear transformation. It's defined to be a linear transformation if for all V1, V2 in the space V and alpha in the space, in the field F, we have phi V1 plus V2 equals phi V1 plus phi V2, and phi alpha V1 is equal to alpha phi v1. So if the mapping respects the vector addition and scalar multiplication in the vector spaces V and W, then that transformation is called linear transformation. Yeah, that's it. That's the generalization of the idea uh, the linear transform. Of matrix multiplication. In fact, this is actually a more fundamental idea. I will give you something as a homework. You see, you may have wondered this weird law of matrix multiplication. So A, B product multiplication. Yeah, you remember? How does this law of the product of two matrices come about? You can check actually that if A is a matrix in Fm cross N and B is a matrix in F N cross P, what it really means, this product is this product is the composition of these two maps. First one from Fp to Fn by the multiplication by the matrix B, then multiplication by matrix A. This composition is in fact the product AB. Yeah, and if you look at this matrix vector multiplication, so if you look at these two maps individually, the map by B, the map by A, yeah, then the natural law of composition of two maps will tell you that this composition is given by that weird product of AB. So show this as a homework. Yeah, but once we have generalized this idea of matrix multiplication by linear map or linear transformation, we can extend this idea of matrix multiplication to many different situations. Yeah, of course, matrix multiplication is an example of a linear map. That is the motivation behind defining the linear map the way we have defined linear transformation. But also, one can define linear transformations for all those exotic vector spaces that we have defined. For example, think of matrices, say square matrices size n cross n, yeah, two square matrices size n cross n. One can define mapping like this. Suppose X is matrix here. This is sent to some A times X for a fixed A. So for a fixed A, which is a matrix in F, which is also in n cross n. So somebody gives me a fixed matrix A, I can define a mapping like this, that X goes to AX. This is a linear map. Yeah, clearly can be checked that this is linear. Not just that, you can define something like, so once again, suppose A and B, two matrices are given to us, both of size, let's say, n cross n. And then one can define a mapping phi from F n cross n. So in fact, let me do it this way. Let me make it a little more general than this. Huh? So suppose A is a given matrix of size m cross m, and B is a matrix of size F n cross n. Then I can define a mapping from m cross n matrices to m cross n matrices in the following manner. If the X here is sent to by this mapping to A X B, this is also linear. You can go ahead and check that this is a linear map. Further, suppose I have, okay, so let us define our symmetric matrices of size n cross n. Yeah, there is this famous map called the Lyapunov map from symmetric matrices to symmetric matrices of size n cross n, where A is some given matrix. This is the symbol for defining this map, LA, where A in R n cross n is fixed given matrix. How is this defined? It sends matrix P, symmetric matrix P, to A transpose P plus PA. This is also a linear map. Yeah, go ahead and check that all these maps are linear. These are your immediate attention problems. Immediate attention problems. Check linearity of each of these maps. I'll give you two more examples. One is this I map from continuous functions from R to R to continuous functions from R to R. How is it defined? If any function is mapped to 0 to t f tau d tau, yeah, this is a linear map. You can check that f1 plus f2 t is equal to integral 0 to t f1 tau plus f2 tau d tau, that is the same as 0 to t f1 tau d tau plus 0 to t f2 tau d tau, which is of course the same as t acting on f1 plus t acting on f2. And likewise t alpha f is going to be 0 to t alpha f tau d tau, which is the same as alpha times 0 to t f tau d tau. This is the same as alpha t acting on f. So it's linear. Similarly, 5, we can define this map d dx from say Rx polynomials to Rx polynomials. This is also linear. So this sends a polynomial fx to df dx. This is a linear map. Once again, you can go ahead and check this. Yeah. So these are all examples of linear maps. Okay. Now, once a linear map is there, two natural questions are not questions, but there are two natural subspaces associated with a linear map, namely the image and the kernel. So let phi be a mapping from V to W, a linear map. When we say mapping, we mean linear unless otherwise specified. Okay. We define kernel of phi to be all those vectors V in V such that phi acting on V is the 0 in W. Yeah, that's the null space of phi. This obviously is a subspace of V. You can go ahead and check that this is a subspace. In fact, checking can be done very easily. Remember what was the test for subspace? So let V1 be in the kernel of phi and V2 also be in the kernel of phi. Then alpha V1 plus V2, okay, and alpha in F arbitrary. We must have alpha V1, V2 acting on phi acting on this by the rule of linear map. This is alpha phi V1 plus phi V2, which is the same as 0 because this is 0, this is 0, this is 0, this is 0. So this is 0 in W. So this implies alpha V1 plus V2 is also there in kernel of phi. So phi, kernel of phi is a subspace. So this implies kernel of phi is a subspace of V. Okay. Then we define the other subspace, image of phi. Image of phi is defined as all those W's in W for which there exists a V in V such that phi V is equal to W, right? So this means this is a collection of all those W's which can be got by some by making phi act on some V. Yeah, pictorially it would look something like this. So suppose this is my vector space V, although I hate drawing these pictures, this can give some misleading informations, misleading pictures. And suppose this is this linear map phi, then this whole space, wherever it gets mapped to, that's the image of phi. Yeah, an image of phi will contain one particular element, the 0 in that field. So sorry, 0 in that vector space, 0 in W. So whatever vectors get mapped to get taken to 0 by phi, this is the kernel of phi. Okay. Now, obviously, image phi is also a vector space, a subspace, right? Why is that so? Um, suppose, okay, suppose we take an arbitrary W1 and W2, both are in the image of phi, and suppose alpha is an arbitrary scalar from the field F. Okay, then because W1 is in the image of phi, there exists V1 such that W1 is equal to phi V1, and there exists V2 such that W2 is equal to phi V2, right? So this now implies if I look at alpha W1 plus W2, then I know that by the law of, by the rule of linearity, this must be true, right? So therefore, there exists this alpha V1 plus V2, for which if phi acts on it, it produces alpha W1 plus W2, which then implies obviously alpha W1 plus W2 must be an element of image of phi. So therefore, by the theorem that states, that characterizes the subspaces, image of phi must also be a subspace. Of course, image of phi is a subspace of the codomain. So image of phi is a subspace here. Is a subspace. So we have these two subspaces. Okay. Yeah. What we are going to see now, and we'll stop the discussion for today, is the rank nullity theorem in terms of this abstract linear transformation, yeah, on abstract vector spaces. Okay, what is that? So let me state that as a theorem, and then I'll give a proof of the theorem. Okay, theorem. Let phi be a linear transformation where dimension V, so it's a finite dimensional vector space. Then, so see carefully, dimension of kernel of phi. Kernel of phi is a subspace of V, which is finite dimensional. So of course, this is also finite dimensional. Dimension of image of phi, this also will turn out to be finite dimensional, but it could be a subspace of an infinite dimensional space. W would be infinite dimensional, I mean. Yeah, but why is this true? We'll see. This is equal to dimension of the vector space V. This is rank nullity theorem for the general case. And the proof, surprisingly, will not require anything about matrices. Okay, but matrices, by virtue of being linear transformations from the vector space spaces that are tuples of numbers, it will follow automatically that this will imply rank nullity theorem, the one that we have seen in the second module of this lecture. But yeah, let us look at the proof of this. Okay, now, all right. So kernel of phi is a subspace of V, as we've seen, is a subspace. And because V is finite dimensional, this also is finite dimensional. Yeah. So let V1 dot 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 up to, what should I call it, Vk, be a basis for kernel of phi. Yeah, such a finite basis will exist. So what does that tell us about the dimension of kernel of phi? It's k. We are assuming that it's k. So it's a basis. Now, by our earlier result that we have proven in the last lecture, not in the last module, but the last lecture, that is lecture 5, that this basis can be extended to a basis of V. So this basis can be extended to a basis of V. So let W1 dot 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 Wn minus k, which is a subset of V, be such that V1 dot 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 Vk, then W1 dot 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 Wn minus k. This together is a basis of the whole space V. So how have I obtained this W1 up to Wn minus k? By the basic basis extension. Yeah. Okay. Now what we claim is the following. Claim phi acting on W1 dot 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 phi acting on Wn minus k is a basis for, any guess, image of phi. Yeah. Now, how do we prove this claim? So we have to show that this is a basis for image of phi. We have to show two things then. First, this is a generating set, and then it's linearly independent. So to show that, first, phi W1 dot 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 phi Wn minus k, the span of this is equal to image of phi. Okay, let's see why should this be true. So let W in image of phi be arbitrary. So I take an arbitrary vector in image of phi. Because it's in the image of phi, this implies there exists a V in V such that phi V is equal to W. But this is a basis, so this guy is a basis for V, which means, but V1 dot 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 Vk and then W1 dot 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 Wn minus k is a basis for V. So therefore there exists alpha 1 dot 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 up to alpha k, and then beta 1 dot 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 up to beta n minus k, all are in F, such that V is equal to alpha 1 V1 plus dot 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 up to alpha k Vk plus beta 1 W1 plus dot 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 to beta n minus k Wk, sorry, Wn minus k, Wn minus k. Yeah, is that all right? But then this means W, which is equal to phi V, must be equal to phi acting on this linear combination, but phi is a linear map. So this is equal to alpha 1 phi v1 dot 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 up to alpha k phi vk plus beta 1 phi w1 plus dot 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 up to beta n minus k phi wn minus k. But you see, v1 up to vk is the basis for the kernel, right? That is how we have chosen v1 up to vk is a basis for kernel of phi. So they themselves must belong to the kernel of phi. So they should go to 0 as phi act on them. As phi acts on them, so this goes to 0, all of this goes to 0. This is nothing but summation I going from 1 to n minus k beta I phi wi, which obviously belongs to the span of phi w1 dot 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 to phi wn minus k, right? One word of caution, I'm using w here, but small w, w1 up to wn minus k. But listen, these are vectors in V only. Yeah, don't get confused. They are not coming from this the codomain space. The codomain is immaterial here, in fact, right? Okay, good. So that means this span is indeed equal to image of phi. So every vector in image of phi can actually be written as a linear combination like this. You may ask that this is equality of sets. Why am I not showing the other direction? Why am I showing that image phi is contained in the span? Yeah. If you think about it, you'll notice that the other containment is actually trivial. That span of phi w1 up to phi wn minus k is contained in image of phi is trivial, because each of these phi w1 up to phi wn minus k by definition is an image phi, so they're linear combinations. So the span is also in the image of phi. Okay, good. Right. So we are done with the span part. What we have to, what remains to be shown is that they are linearly independent. To show that phi w1 dot 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 up to phi wn minus k is linearly independent. Okay. Now, why is that so? So you know the trick of showing linear independence. Yeah. Take linear combination, equate it to 0, show that all the coefficients must go to 0. Let's do that. So suppose alpha 1 phi w1 dot 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 up to alpha n minus k phi wn minus k is equal to 0. By linear map, this means phi acting on alpha w1 plus dot dot up to alpha n minus k into wn minus k is equal to 0. But what does this mean? This means this vector must belong to kernel of phi, isn't it? Because phi of this is going to 0. But if this belongs to kernel of phi, and we have already a basis for kernel of phi, so this means alpha 1 w1 plus dot 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 up to alpha n minus k wn minus k must be equal to some gamma 1 v1 plus dot 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 gamma k vk. Yeah, but these vectors together, v1 up to vk and w1 up to wn minus k, they are linearly independent. So this linear combination going to 0, that is gamma 1 v1 plus dot 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 up to gamma k vk minus alpha 1 w1 minus dot 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 minus alpha n minus k wn minus k equal to 0 implies gamma 1 equals gamma 2 dot 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 equals gamma k equals alpha 1 equals alpha 2 dot 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 equals alpha k. All of them is equal to 0. This is because v1 vk w1 wn minus k is linearly independent. Yeah, but this is what we wanted to show. Alpha 1 up to alpha k is equal to 0. Alpha n minus k, I'm sorry, should be alpha n minus k. Alpha 1 up to alpha n minus k equal to 0. Yeah. Yeah, is that all right? So then they're linearly independent, which means they must be a span. So this implies this set phi w1 dot 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 phi wn minus k is a basis for image of phi. Yeah, this was a larger thing. In fact, we have shown something larger than what we really wanted. This then further implies that dimension of image of phi then must be equal to n minus k. Okay, but what was this n, by the way? Yeah, but then dimension of v is n. Yeah, because the basis has size n. Dimension of kernel of phi is k. So then this implies dimension of kernel of phi plus dimension of image of phi is equal to dimension of v. Yeah. When you apply this to, so this is what we wanted to prove, in fact. When you apply this to matrices, you get back your rank nullity theorem. Yeah, indeed. This is, of course, nullity. This is n. Yeah, so if A is a matrix, so if A is a matrix in F m cross n, then A is in fact by multiplication from the right by row by column vectors. This is a map from Fn to Fm. Yeah, so kernel lies here. And dimension of image of phi, you see, for this image of this map is nothing but, what is it? This is nothing but the column span of A. So in fact, the dimension of the image of A is nothing but the column rank of A. So this theorem in fact shows that, so a corollary of this applied to the special case of matrices is that dimension of kernel of A plus column rank of A is equal to n. But our row reduced echelon form shows that, and what we have seen earlier, that row rank is equal to column rank. So this is just rank. So this is dimension of kernel of A plus rank of A is equal to n. That's rank nullity theorem. If you don't want to use column rank is equal to row rank idea, then you can just say that, okay, dimension of kernel of A plus column rank of A is equal to n. From row reduced echelon form analysis, we know that dimension of kernel of A plus row rank of A is equal to n. Together they will imply that row rank is equal to column rank of A. Yeah, I hope this is understandable. Okay, try and think about this. I'm not giving any more immediate attention problems this time, because last lecture had quite a few of them, and because of the quiz, I think you may not have solved them yet. So do solve them. So therefore, less load for this lecture. Okay, so see you in the live sessions, and then once again see you in lecture number 7. Till then, take care. Bye bye.